Welcome to Sunsets TV and this episode of Eureka. In this episode, we are going to have a very interesting conversation with Dr. Ramadass, who is the Director of National Institute of Ocean Technology in Chennai, a constant unit of Ministry of Earth Sciences. They are about to launch a very major national program. Just as Chandrayaan went and explored Moon, Mars Orbiter mission, or popularly known as Mangalyaan, was launched to explore the Mars, and Gaganyaan is expected to be launched to explore the outer space. They are embarking on a very major program called as Samudrayaan to see the underwater, where not many people have gone. In this episode, we are going to talk about his work, the Samudrayaan, and major activities of NIOT, like prevention of early warning of tsunami. So thank you for being in this show. Welcome to Sunset TV and this episode of Eureka. But before we embark on our conversation on Samudrayaan, which is going to be really a very interesting conversation, maybe let me start with your doctoral work in Indian Institute of Technology, Madras, Chennai. Your work as a C is on the area of acoustics, ultrasound. And ultrasound is something that we have heard when we are talking about pregnant women doing prenatal testing, or sometimes maybe for medical imaging. I mean, we use ultrasound. So, how is ultrasound is a technology that is useful in underwater, deep oceans? How are they connected?
My doctoral work was on studies on high temperature superconductors.
Okay.
So I used acoustic velocity and attenuation for studying the superconducting phenomena in high temperature superconductors.
Okay.
So basically, I used ultrasonics for studying superconductivity. So I developed the interest in this work. Then I realized that in ocean or in water, electromagnetic waves cannot travel long distances. At the best, they can only travel some tens of meters. Now, only radiation that can penetrate long ranges in water is sound. Okay. So basically, underwater, you use sound for seeing. Of course, it is very slow when compared to light, and the information that it can carry is very small again when compared to electromagnetic radiation. But that is the only radiation that is available to you in oceans for exploration. That's
two clarification maybe I'll seek here. And when you are talking about sound, is it like for example in the range of human sound? Because humans make sound in a particular range. I mean, ultra sound is something in a different range. What is that range? That is number one question. Number two question, you said that the speed at which the waves move is much less compared to the electromagnetic wave. So what is the kind of comparison there? These are two important questions, let's say, to begin with.
The sound travels with around the speed of 330 meters per second.
Okay.
Whereas if you see velocity of light, it is 3 lakh kilometers per second. So that is the difference. So, and light can penetrate only some tens of meters in water, whereas sound can penetrate even tens, if not hundreds of kilometers into ocean. But again, the frequencies, coming back to frequency, human ear is sensitive between 20 hertz to 20 kilohertz. But in ocean, depending on the range, we mainly use sound in the range of kilohertz. But if you want long range, you have to use low frequencies. But if you want short range but high resolution, then you have to use high frequencies. Basically, generally we use ultrasound for exploring the oceans.
Very, 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 very interesting. So after your stint at IIT, where you worked on this area and then found that there is a relationship between the kind of thing that you are developing and the NIOT's quest, you joined NIOT and then started developing acoustic based instruments. So can you tell us what are the kind of areas that you worked on, explored, developed in NIOT?
Yeah, we started with developing small instrument called acoustic tide gauge. It is mainly used for measuring tide levels in oceans very accurately, both phase and the amplitude. We developed these systems and we installed them at different places, including Port Blair in Andamans. So when really the tsunami happened, this tide gauge we installed at Port Blair could record the earthquake and the tsunami together, and it gave us a lot of data. And for some time to come, it also served as a sort of early warning system also. Later, we went into developing many other instruments like some special kinds of sonars, establishing acoustic testing facility and all. And then we started giving instrumentation and acoustic support to underwater vehicles and exploration systems.
So, which means that like an underwater vehicle, like for example, if you are looking at an aircraft, it is fitted with a radio device. Today, even trains, pilot carry a walkie-talkie to communicate with the nearest railway station. So, you are saying that the underwater vehicles carry sonar equipment for communication?
Yeah, there are actually parallels. For example, sonar is an underwater counterpart of radar.
Okay.
Similarly, like GPS, we can use GPS. When you keep an equipment or you send a vehicle underwater, you don't know where it is. So there is something called underwater acoustic positioning system, which really tells you where it is and how it is navigating, what is the speed and all. Similarly, like modems we have for carrying the data, we also have underwater acoustic modems. So there is a parallel, perfect parallel, but there are some limitations. Like I told earlier, sound is very much different from light.
One question that many people might have now is that why not put a cable? I mean, after all, there is going to be a mothership on the surface. You are sending a vehicle below the water. It's not like a space where you are about 100 kilometers away. But here you can have a mothership, and then you can put a cable, and then things are solved.
Yeah, actually, we do use cables. We call them actually umbilicals. This umbilical is a composite cable which can not only bear the load, but it can supply the power, and it can also send the signals and receive the data back. Okay, so we call them umbilical cables. But the problem is there are some limitations. Underwater, any cable or any device you put there, it faces a lot of drag or resistance. So whenever the vehicle moves or there are currents, so it offers a lot of resistance. And second thing is it limits the range of the vehicle. So it limits to really, see at 6,000 meters, if you have a 6,000 meter cable, the range is limited to some tens of meters. So that it has a severe limitation on the utility of the vehicle.
So although you use the tethered vehicle, that is only for certain depths, but when you want to really go underwater, I mean, you have to use some kind of a robotic vessels, which will kind of work on its own. I mean, without directly connected to the mothership. That's what is a system that would be working, right?
Yeah, but even at very high depths, we use tethered vehicles with some limitations. But if you don't have a tether, you have to necessarily pre-program it. So you don't get to see what it is doing or what it is seeing. So you can't even intervene. Okay, you get some rudimentary data, but you don't know exactly what is happening there. So you get the information only when it resurfaces and you can retrieve the data. So there are some limitations in untethered vehicles, and there are some limitations on the tethered vehicles.
Right.
Unlike space, where you can control a Mars rover sitting on the Earth, you cannot control a vehicle which is at 5 meters.
That's a big challenge that you have. Let me move to another area of your institute work, from your work to institute work. Your institution has number of research vessels. I mean, in that people from your institution, scientists go to sea and conduct many sorts of experiments or maybe maintenance. So what do you actually do when you go on this kind of expeditions?
See, we have a small fleet of vessels. There are different vessels for different purposes. For example, for coastal research, we have smaller vessels with lesser endurance and with less space for the scientists. Okay, but it is fitted with some equipment which is suitable for the coastal purposes. So maybe a team of 10 scientists can embark on that one and go for a few days into the ocean. They can survey, they explore the ocean and survey the seabed, collect some samples, okay, and then they can come back. But if you want to go for higher depths, in the sense of longer ranges, we need a ship with longer duration and better equipment. So we have a flagship called Sagar Nidhi, so which is actually a 100 meters long vessel, which can take around 25 scientists apart from the crew. Okay, so we load our equipment, all our equipment, through our Chennai port after crossing the immigration, customs, and all formalities, and then we load our equipment and we go into the sea and we explore the ocean with by launching our equipment, retrieving it and all. But there you are on your own. Okay, like you don't get a second chance. Even if you forget to carry a bolt and nut, you won't get it. So you have to be extra careful when you go for an ocean exploration. You don't get a second chance that easily.
Yeah. So I was told that one of the interesting thing when you go on this kind of icy expedition is that half of them are seasick and half of them are homesick, right?
Yeah, it's an old joke actually, because when we go on this kind of long cruises and all, depending on the weather and all, many people fall sick, but it's not actually, it is not life-threatening or anything, but it can be of high inconvenience and all. But also in the long, when you sail for maybe 40 days, 50 days and all, you get into all kinds of problems actually.
Yeah, it's a good banter within an institute where, but of course, every scientist is lured again and again. Nobody refuses and takes on this expedition. That's what I suppose you would have seen all your career, right? I mean,
yes, we are not sailors. We are not trained sailors. We are basically scientists. But every scientist in NIOT loves to go for scientific explorations on board research vessels, and nobody refuses that chance to go.
That's very interesting, and this is where we will take a very short break. After the break, we will continue with the conversation, and we will explore the most important work that NIOT is taken up on its shoulders right now, Samudrayaan.
अनुच्छेद 48A के तहत पर्यावरण की रक्षा और सुधार तथा देश के वनों और वन्य जीवन की रक्षा करने का प्रयास करना राज्य की जिम्मेदारी है।
Welcome to Sunset TV and this episode of Eureka. And in this episode, we are having a very wonderful conversation with Dr. Ramadass, who is the director of National Institute of Ocean Technology, Chennai. A constant unit of Ministry of Earth Sciences. They are embarked on a very important, very national program called Samudrayaan. They are going to go to a place where not many people have gone, about 6 kilometers below the ocean. So one question that comes when we talk about Samudrayaan is, after all, you can send a robotic vehicle. So why do we need to send humans below that 6 kilometer, and why the Samudrayaan?
Yeah, as we discussed earlier, we can send robots, and we have been sending for last 2 decades. NIOT has been sending number of unmanned vehicles to 6,000 meters for 10. But the problem is, if you have a cable, your range is limited, and a lot of drag is there, so you cannot reach the places you want to really reach.
Okay.
Of course, you can intervene, you can see with cameras and lights and other things. But if you send an untethered robot, then you don't get to see what it is doing or what it is observing, and you cannot even intervene because there is no communication, and this acoustic communication is very rudimentary. So,
Just a point here. I mean, like, for example, nowadays we are seeing in the media that, for example, in Mars rover, when it sees something very interesting, by chance, you are able to control from ground and then make it go there and then explore it further. But you are saying that if it is underwater robotics, that is very, very difficult, right?
yeah, you can control a Mars rover sitting from here with a little bit of delay. Uh, 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 but in underwater, because you have only sound as the communication that is, facility, so you don't get to really control the vehicles as you want.
Okay.
Either you have to have a tether for better control and intervention, or you have to pre-program it. As you can get some kind of information back, but you don't have much control over that. So only if you combine these two capabilities, that is human scientific submersible, where you can keep a human being in the loop, where he can see what is happening, he can take decision, or he or she can really intervene, collect samples, observe. So that is actually, unlike space, the role of man is more important in this ocean exploration.
Okay. Okay. Deep ocean, the human being going there would be taking us one step further than the robotic mission. That's what you are pointing out. So when we look at, for example, the 6 kilometer, which is the kind of benchmark with which we are going on this first Samudrayaan, maybe we'll go deeper further, but initially we are looking at the 6 kilometers. What challenges, major challenges are there when you're talking about 6 kilometers?
The first thing that comes to my mind is the pressure. So at 6 kilometers, you have 600 bar pressure.
Okay.
So when a space vehicle goes up, the pressure difference is only 1 bar. So inside it is only 1 atmosphere, outside it is 0. But when a vehicle goes underwater, each 10 meters adds 1 atmospheric pressure actually to that. So at 6,000 meters, you have 600 bar pressure. So if you put anything there, the triaxial pressure acts on that one and it gets crumpled.
So let me just ask a question. Like, suppose I go to 6 kilometer depth and carry let's say a can of aerated drink. I mean empty. So if I keep that empty can, what will happen to it?
See, if the water can enter that can, nothing happens because inside and outside there is same pressure. But if it is a sealed can, actually it crumples. It becomes like it gets crumpled like a sheet actually. So
okay, so something like a puppet. A can will be compressed into a puppet. Huh?
Yeah, you said it. Yes.
So that is really a very challenging place, right? I mean, so when you said this pressure, so what other major challenges are there when you are going that deep?
Second thing is that it is actually pitch dark there because you beyond some maybe 30-40 meters, you don't see anything there. So you have to carry your own lights and cameras, and the visibility is very much limited to few meters.
Okay.
Third one is the temperature. So beyond 1,000 meters, the temperature falls to even 4 degrees, and at 6,000 meters, you can even see around 2 degrees centigrade. So these are the problems. And there is no acoustic, there is no positioning system, there is no GPS, you don't know where you are. and there is no communication with the mothership except for some acoustic communication.
Okay.
And these are the challenges. And the pressure is not pressure, temperature, currents, all these things are not uniform. It's a dynamic medium. It is ever changing medium. So that is a challenge.
That is the important challenge. So when you are to build a submersible for this, I mean, a craft which can go and survive with them, I mean, that means then there are huge challenges in design, right? So what is the craft that you are designing? Can you describe to us?
Yeah, the vehicle we are making, it primarily consists of a sphere.
Okay.
It's actually a special alloy, titanium alloy sphere with some 3 viewports, perspective viewports with a hatch. So it's a thick titanium alloy sphere. It's a challenge to really make it and weld these components into a sphere and all. It's a special technique that is required. So inside this thick titanium alloy human sphere, 3 human beings can sit with what we call short sleeve environment. It's a 1 bar environment. So you have to replenish the oxygen in that, and you have to remove the CO2 that is accumulating, and we have to maintain a near normal temperature and pressure inside the sphere.
So why in a sphere shape? I mean, after all, different crafts have different space. So why this underwater craft has a sphere shape?
Sphere shape, it offers the best structural stability. So with this and otherwise it has to be highly like thickness goes up, weight goes up, and also a sphere shape has a lot of advantages. So we studied different materials, different shapes, and we arrived at a spherical sphere of titanium alloy.
Very, very interesting. So now when we are embarking on to this uncharted terrain, I mean, not many people have gone, not many countries have gone that deep. Obviously, you need to establish facilities in your institution for testing, calibration of all these components, various components. And I'm told that you have established a pressure chamber, which will simulate the condition under the deep ocean. So can you explain to us what is it, what exactly you do there, how is it helping the whole project?
Yeah, we have established a facility called Hyperbearing Facility. Okay. So we can keep a component or equipment inside and close, and it is filled with water, and you can create a pressure up to 900 bar, which is equal to 9,000 meters water depth. Here, whatever actually any system, underwater system has some tens of subsystems and components. So each system has to be tested at that pressure before integrating it into a final system. So each one we had to carry to the ocean and beyond I mean 6,000 meters water depth, we had to keep it and then test it. So it is really a time-consuming process, and it's actually we had some challenges in that. So we established the system. Here we can keep the equipment inside the chamber. You can pressurize it and simulate that depth. Once it is qualified, now that is ready to be integrated into system. So it really saves the time, cost, and energy.
That's a very interesting point. So similarly, you have some underwater calibration tank, right? I mean, to test your communication equipment and so on.
Yeah, we call it acoustic test facility. So it is actually a 7-meter deep tank, specially designed tank with controlled conditions. As you know, each acoustic instrument, underwater acoustic instrument, carries a number of acoustic transducers which convert electrical energy into sound energy and sound energy into electrical energy. So each of these transducer has to be properly calibrated at what frequency it is sensitive, and with if we give 1 unit of electrical energy, how much acoustic energy comes out. Similarly, if 1 unit of acoustic energy impinges on that, how much will be the electrical energy that is generated, and in which direction it is sensitive. All these things have to be precisely calibrated before that is integrated into any sonar or equipment. And NIOT has that facility to do for our own internal purposes, and many other national laboratories and industries also use this facility.
Okay, very nice. So now these are two important facilities that you have created for the Samudrayaan project. What other major activities are right now taking shape in your institute for this Samudrayaan project?
See, it has different components. For example, life support system is a very important thing. So three human beings should be able to breathe for at least 16 hours normally under normal circumstances. If they are stuck there because of some problem, then this should be extended to 96 hours before they are rescued. So we have to release the oxygen and CO2 levels build up. So we have to actually remove the CO2 from that small space. So we need to have some kind of systems for, we call it scrubbing, CO2 scrubbing. So it is called life support system. And we should also have some other systems which can be used in under emergency conditions. That is one part of it. Then second thing is to take the system down, you need to have some propulsion systems. Something like thrusters, we have to use like propellers and all. Sometimes ballast systems which can take and all, and they should have enough power. So we have some specialized batteries for powering the system. So, and all these things should have proper redundancies. So, and we also use drop weights for, we take the weight for going down and we drop the weight for coming up. So there are so many control systems. All these things are being developed in NIOT right now.
Okay. So what is the timeline now? I mean, of course, the COVID really created a havoc in our whole plan. So now, kind of, we are coming out of the COVID pandemic situation. So, what is the kind of timeline that we are looking at? What are the major events that will be happening in next, let's say, a few months?
Yeah, our target is 2024 for launching Mascha 6000. That is the name of our vehicle, underwater manned scientific submersible. Okay, so that is 2024 is our deadline. But before that one, we have to, each system has to be tested. For example, first we are launching a 500-meter sphere before we go for 6,000 meters. So we are going for a 500-meter sphere. So that we will be testing. And this life support system has to be tested. Tests are right now going on in our laboratory for keeping the three human beings inside and then see how this oxygen is consumed and CO2 is generated and all. Similarly, this batteries, every component has to be procured. And from design stage onwards, it has to be certified for manned rating.
Okay.
So that work is going on. So there are many intermediate steps, and we have some short-term goals. Means we'll be demonstrating that completion of each stage. Then the integration takes place. Then the trials start from 15 meters or even less than that one. So we will go to 6,000 meters in phases. When we say 6,000 meters, that doesn't mean that in one day we will be reaching that one. So we have to start from shallow waters and reach that.
Slow, step by step to, like similarly, outer space also, first we explored near Earth, the lower orbit before we went to moon or deep space. In the same way, I mean, you need to go step by step to get the thing. It's a very, very exciting project. I mean, as somebody said that we have photograph of moon, all parts of the moon, very detailed image of a moon surface. But somebody said that we don't even have 10% of ocean floor surface images. Most of the things that we see in maps are largely guesses. That's what somebody said. So it's a area where we have not explored at all. Not India, not any other country. Only very few countries around the world are embarking on such a major mission. And your institute as spearheading this on behalf of India. So we want to thank you on behalf of Sunset TV and the viewers of Eureka for this major project, and wish you all the best for this work. And thank you for your time for this show. Keep watching Eureka. We'll come back with another episode next week, same time.